Whenever you have a stoichiometry problem, the reactants that are given are either given in stoichiometric quantities or with a limiting reagent. Stoichiometric quantities means that exactly the right amounts react so that all of the reactants are used up at the same time. That means there's nothing left over of one or both reactants. Stoichiometric quantities mean that if you have a 1-to-1 mole ratio, exactly 1 mole of each reactant was reacted. This almost never happens. Almost always you have one thing that is excess. For example, in the silver lab, we made sure that the sodium chloride was excess. We made sure that we used extra of that. Almost every case, that's the case. In the practice problems of the day, there was that problem that said there was 4.81 kilograms of hydrogen and it reacted with excess tungsten 6 oxide, I believe. That means that these were not in stoichiometric quantities. In fact, that there was a limiting reagent. A limiting reagent or a limiting reactant is the reactant that's used up first, the one that limits the amount of products that can be formed. It's kind of like the ingredient that you have the least amount of at home when you're, following a recipe. Everything else is excess. The excess reactant or reactants are the reactants that are present in quantities greater than necessary. In other words, with that tungsten oxide and the hydrogen example, the hydrogen was the limiting reagent or reactant, and the tungsten oxide was in excess. Sometimes a problem will tell you that there's something in excess, and sometimes you have to figure it out. When you have to figure it out, you're going to follow a series of steps, which is clearly on the next slide, not this one, because this slide says theoretical yield. Theoretical yield is the amount of product that can be formed when the limiting reactant is completely consumed. It's the maximum amount that's produced. It's the amount that if everything went perfectly right in the lab, the amount that you calculated through stoichiometry would be the amount that you got. Now again, that almost never happens, but we always calculate through stoichiometry how much we would expect to get. It's this expected yield would be a synonym for theoretical yield. Here is the slide with steps. In the steps for a limiting reagent problem are almost the same. You have one extra little thing to figure out. But we're still going to start with a balanced equation. You're going to convert masses of reactants to moles. Now, in a limiting reagent problem, you're going to find that there are going to be 2 givens, not just one. You're going to convert both of those givens to moles. You're going to convert both of those moles using the mole ratio to find the number of moles of B that would be produced, that would be possible. From that, you'll see which one will produce the least amount of B, and that's your limiting reactant. That will have a smaller number of moles. And then you'll proceed with that last step of stoichiometry, going from moles to grams, using the reactant that's limiting. It's the one that was the smaller number. We're going to look at an example. So nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide at high temperatures. It also produces copper and water. In this problem, you can see that there are 2 givens, 18.1 grams of ammonia and 90.4 grams of copper oxide. So if we want to know how many grams of nitrogen will be formed, we have to figure out which of those 2 givens to use. So you can see here, I've gone ahead and shown the work for the first 2 steps of stoichiometry using the ammonia. We convert the ammonia from grams to moles, and then moles of NH3 to moles of nitrogen. And that would produce 0.531 moles of nitrogen if the ammonia was limiting. This mole weight, I think, is the IB mole weight. I think AP would be 17.034 or something similar to that. So that can vary, but I think with significant figures you end up with the same number of moles. Now we just don't know if that one's limiting. The copper oxide could be limiting. So we would go ahead and do the same thing with the copper oxide, converting copper oxide to moles, and then using the mole ratio to figure out how many moles of nitrogen that would produce if, in fact, the copper oxide was limiting. So based on that, that would produce 0.379 moles, possibly. So now if you look at that, the copper oxide produces fewer moles than the ammonia, which means that the copper oxide is the one that's limiting. The ammonia can't all react and produce 0.531 moles if the copper oxide would only produce 0.379. Only one of those can totally react. And so in this case, the copper oxide is the limiting reagent. That means that everything that we just did with the ammonia, the NH3, we can ignore. Unless a problem asks us to solve for how much ammonia is left, we'll get to that later, we're going to ignore it. We're going to go and proceed with the stoichiometry. We're going to do the last step of stoichiometry using that copper oxide to figure out how many grams of ammonia, or I'm sorry, of N2 would be formed. So here are those same two steps, the 0.379 moles of nitrogen that we're using, and then we'll multiply that by the mole weight of nitrogen, 28.02. And so in this problem, the 10.6 grams is our final answer of nitrogen that would be formed. You're probably thinking this right now, so I'm not going to do any more stoichiometry problems. Now it's your turn to go try those on the practice problems number 2 sheet and upload a picture of your work onto Classroom to count for your virtual learning experience. Before you do that, a word about percent yield, because I know there is a problem, at least one problem like this on there too. Percent yield is not the same as percent error. Percent yield is the amount that you collect based on how much you should collect. Experimental yield is the amount that you collect in a lab experiment. So before we were talking about theoretical yield and the amount that you would expect to produce if the stoichiometry went perfectly. The experimental yield is reality, how much you actually do produce in the lab. And the percent yield is the ratio of the two. Experimental over that theoretical times 100. It's not the same as percent error, but if you had a high percent yield, you got a lot of what you should have, then you'd probably have a low percent error. So they are related, but not the same. Lastly, you'll find that we will almost always, in class and in industry, percent yield is almost always less than 100%. And there are about 3 reasons why. One is because many reactions are reversible. We always think of them as straightforward, going the forward direction, but many of them will go backwards at some point, reaching equilibrium, which we'll cover in another unit. Also, sometimes it's difficult, as we know, to recover 100% of the product. Sometimes we lose things to the filter paper. Sometimes we breathe too heavily on our product, and we can't recover 100% of it. And the third reason is because most reactions are more complex than what we are studying at this point and what we are writing as a straightforward forward reaction of like A plus B yields C plus D. A lot of those reactions as C and D are forming will keep reacting into further reactions. And that can reduce the yield of, the initial products C and D, for example. We'll cover percent yield a little bit more as we analyze our data from the Silver Lab, but go ahead, use that example with the nitrogen, the copper oxide. Use that example to give those other stoichiometry problems a shot. And I hope you enjoy your semi-day off on Thursday.